Welcome back to Arxflix. Today, we're diving into an innovative paper titled Learning Transformer Programs. This research introduces a unique methodology to train transformers that are inherently interpretable by design. This figure illustrates the concept: a modified transformer that can be trained on data and then automatically converted into a human-readable program. Think of it as decoding a neural network into simple Python code. Let's explore the main points of this exciting paper. Recent research in mechanistic interpretability involves dissecting transformer models to understand their inner workings. However, this manual process is labor-intensive and doesn't provide a complete picture. Prior work such as RASP aimed to map human-written programs to transformer weights, but this paper flips the script. Instead of compiling programs, it trains transformers that can directly output interpretable programs. The authors introduced transformer programs, models that implement human interpretable algorithms. They achieve this by imposing constraints on the transformer weights, ensuring they can be mapped to a family of human-readable programs. After training, these programs can be decompiled into Python code, allowing easy debugging and analysis with common code tools. To make the transformer interpretable, the model maintains a disentangled residual stream. The token embeddings encode a fixed set of discrete variables in orthogonal subspaces. Each module reads a fixed set of variables and writes new ones to a dedicated address. This way, each layer reads specific information and writes its output in a clear, isolated manner. Next, the method constrains each module to implement understandable, rule-based mappings. Attention heads handle select and aggregate operations, determining query key relationships and combining values accordingly. Optimizing these transformer programs involves discrete program weights. The loss is minimized using the Gumbel reparameterization technique. Here's an example of a categorical attention module. The first layer's attention mechanism maps letter tokens to numbers preceded by the same letter. After training, the transformer is converted into an equivalent Python program. Each attention head translates into a predicate function, mapping query key pairs to Boolean values. The researchers validate their approach on several tasks, including algorithmic problems and NLP benchmarks. For instance, in in-context learning, the model correctly learns to output numbers based on preceding letters. The results are impressive, showing near-perfect accuracy on some tasks. However, for more complicated tasks like most FREC, performance varied. The paper also explores how the transformer distinguishes between different entity types in named entity recognition tasks. Attention heads help in making contextual predictions about entities like locations or organizations. This research marks a significant step towards making machine learning models more interpretable. By converting transformers into discrete programs, we can better understand and debug their behavior. While challenges remain in scaling and optimization, this approach opens new avenues for creating inherently interpretable models. Thanks for watching Arxflix. Don't forget to subscribe for more quick summaries of cutting-edge AI research. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.